So let's get this party started. All right, yeah, it's the 16th already. Dang. All right, so a couple quick announcements before we get going here. Sorry, our homework 4 is going to be going up. I'm sorry I didn't get that up last Thursday. Just because long story, but basically because I'm had to reorder stuff from last semester. All my it's really complicated how you move homework questions around in Canvas and all this kind of behind the scenes drama. It's not like drama, but it's just confusing and it takes me a little while to get that. And I thought it'd be quicker than it was and it took me longer. And so I'm a little bit slow on getting those up, but I will get those up. But as I mentioned before, I will always give you at least a week to do all the homework stuff. So that should be going up today and should be, I'm hoping it goes up today. I'm swamped until till 5 o'clock, but I'll try and get that posted today. But I will send out the announcement that it's up and that you'll have a week to do it. And yeah, should be good to go on that. So what we're gonna do is we're diving into, and I don't know which chapter that is. Maybe it's chapter 4, I think, at this point. So chapter 4, which is going to be on how we hear. So this is one of my favorite sections. I love this stuff. I think this stuff is so cool. This is where we start to really see the convergence of all these different disciplines of biology and physics and science and stuff. All these things are going to start coming together, and I think this is what I think is one of the coolest areas of how we actually start to combine all this stuff. Because I get the vibe, with the decibel stuff, it's not something that you use you do use them every day, but you don't do the math every day. Whereas something like we listen every day. And so I think having some understanding of this really will carry you. This is the big trivia section. This is a lot of stuff that we're going to talk about throughout this section is going to be oh, cool. So that's how that works. That's that's what I really want you to get out of this. There's the book is actually pretty deep. It goes in some pretty deep details in some of the pretty complex subjects. I'm not going to go into hit every single thing in the chapter. So while I do think you should read the entire chapter, it's great. I'm not going to be using a lot of I won't say esoteric, but I'm not going to use all the content through the entire semester or through the entire chapter. I'm only going to be using what I think are the important parts that are pretty relevant to what we're going to be talking about later in the class, but also just stuff that will kind of make it understand how this stuff works, how on a day-to-day level. So that's what we're going to be working on here. So we're going to start with psychology, ear physiology, middle ear, cochlea, and place theory. So today's going to be kind of mostly anatomy and physiology, and then next class, we're going to start in on more of the perception of stuff. And then I can't remember so we're doing 3 days on this stuff. So it's all this week and then one day next week. And so I can't remember how it goes. I have to look. It's been a while since I've reviewed this. So, but like I said, I've been doing this particular, this stuff I've been teaching for a long time. And so I love how this stuff works. So let's talk about this idea, psychoacoustics. So you'll hear this term sometimes used around here. And when we talk about acoustics and then we talk about psychoacoustics, this actually kind of goes even back to what we were talking about on the first day of class. If a tree falls in forest, no one's around to hear it, doesn't make a sound. And this idea of going back to this definition of what we call sound. And so sound, we could say that the vibrations in the air, but actual sound is a perception. It's how we perceive this thing. So, and to a greater degree, that's what psychoacoustics is. Psychoacoustics is how our brain interprets the sound. And we're not going to go that far into it. We're going to get into it a little bit. But psychoacoustics is this whole huge other massive branch of this. Is not only just what the sounds are and how they get to their ear, but how we interpret the sounds. Because and we're going to spend a lot of time talking about this today, is that basically we're turning these air molecules moving back and forth, or maybe this sound generator, what do I have here? Something from last time. I've got my little tuning fork, right? So my little tuning fork here it's pushing and pulling on the air. These little tines are moving back and forth, and they're pushing and pulling on the air, which is then pushing and propagating through, hits my eardrum, moves my eardrum back and forth, and it goes through this really complex process to get to the point where my brain can understand this and how we actually are able to interpret that. And so that's what psychoacoustics is. And so we'll, again, like I said, we'll talk about this in just minor detail because that's an entire PhD degree to get deep into psychoacoustics, but I think it's like worth noting that that's how we perceive sound, is like what the perception of it is, and that's where I think things get really fascinating. So we're gonna go right up to that point, and then we're gonna like, oh, stop right there. But I think this is where things it's really neat. So cool. So yeah. So Link, you're saying like basically it's a way longer chapter, and indeed this chapter is a lot longer. Like I said, I'm not going to be hitting all the stuff in the chapter. I'm only going to be hitting the highlights of what I think are important. And so what I'm going to ask you for in terms of homework questions and like quiz questions or whatever, midterms and finals, is only the stuff that I cover in class. I'm not going to cover something in class and then not cover something in the book and then ask you to like know something out of the book, unless I say that. But generally speaking, like anything that I think I'm only going to ask you about stuff that I am working with in tandem with the book. So just as to ease your mind a little bit. Okay, so what we want to do is let's take a bird's eye perspective on just this idea of how we hear sound, and we're going to talk about things like frequency and amplitude, and then we're going to drill down and talk about the physiology of this thing. So let's take a step back and let's talk about the range of human hearing. This is something we throw around a lot, and when we talk about how we hear, like we talk like how loud the range, how loud we hear it, and how wide we hear it, like in terms of frequency. So let's start with frequency. So when we talk about this, we want to talk about like the frequency range on which we hear it. Now, everybody's going to be built a little bit different, but we've kind of come to over the I don't know how long they've been testing it, but they've been doing hearing testing. They're going to narrow this down into like an average range. And so what we typically say is that humans can hear from 20 to 20,000 hertz. So and here I said 20 kilohertz. So kilo means thousand. So 20 hertz is 20 hertz is 20 hertz, and then 20 kilohertz is also the same thing as 20,000 hertz. So just to make clear, what those two things are. And if you recall, back when we did the V equals F times lambda equation, we could say that, okay, well, we know that the 20 hertz correlates to a 17.2 wavelength, so it's really long. And then 20 kilohertz or 20,000 hertz correlates to a wavelength of a sound that's about of a wave about that long right there. So 1.72 centimeters. So that's about the range in which we can hear it. Now, of course, I would high five anybody in this room, well, in this Zoom call, that actually hear 20 hertz. Hearing 20 hertz is pretty stinking low. We can't really hear it. You can kind of feel it, but we don't perceive it too much. But if you were to say 25.5, that's just kind of like a tough number. So it's just easier and cleaner for us to say 20 to 20,000 hertz. And also on the flip side, 20,000 hertz is pretty stinking hard to hear as well. Like, you have to have pretty good hearing. And we'll talk about hearing loss. I think we talked about that in the third day. Talk about like how hearing loss affects us. But like, I can't hear 20,000 hertz. Y'all can probably, like, you're younger, and so your high frequencies decline with your age over time. So like, you have likely people in this class have better hearing at the high frequencies than I do, at the higher frequencies. So, but we'll talk about that in a little bit here. So so we say 20 to 20,000 hertz. Yeah, that's what we say. So we can also divide this up in terms of octaves. So we can say that we can see 10 octaves, and I'm kind of steering away from the use of octaves in this class because that's a musical term. That's not necessarily so much of an acoustics term. So, so when I say one octave, so from 20 to one octave from 20 hertz would be 20 to 40 hertz. And then 40 hertz to 80 hertz is another octave. And then 80 hertz to 160 hertz is another octave. And 160 to 320 is another octave. 320 to 640 is another octave. And going up there. So it's basically an octave doubles every single time. But 10 octaves is kind of, if we want to talk about this, the range in which we can hear the human hearing is 10 octaves, which is massive, say, compared to our visual system. So in our visual system, so we also see, so we can hear frequencies, but we can also see frequencies. And so we see frequencies in terms of light. The wavelength of light is what is the frequencies. And the wavelength of light determines what our color is. So like the low frequencies are red and the high frequencies are violet, but we can see everything in between those in terms of color. But if we look at the range in which we do that, we can only see less than 1 octave of light compared to our hearing, which is massively huge. So this is like pretty an impressive feat. But there's going to be to make this thing happen, we pull a couple shortcuts here, and so we'll have to see how this works. Well, I guess like when I talk about this thing with the light. So even though we can only see one octave of light, we can see really well within that one octave. We can differentiate a ton of different colors in that tiny spectrum of light, because probably, we're one of the most visually acute animals on the planet. That we're a visual being. Say, compared to say something like a fish, or to say something like some of these other animals, or even like my dog. Like my dog can see that she has pretty good light and dark contrast, but she can see some reds, but she can't see greens and blues and all these other kind of things that go on in there. So that's when we talk about rods and cones and a little bit of that. And I'm not too good on visual biology. I'm not entirely sure how all that stuff works. Like, it's been a long time since I've had it, since I've had biology in high school, that I know how that works. But what we can say though is we can hear a massive range. We can only see within one octave, but we can see really well within one octave, specifically greens, right? Because we live in a green world, we're able to differentiate lots of different shades of green. We're really good at differentiating green. That's just one of the things we do. So, oh no, you popped your eardrum. That sucks. Oof, that's awful. Okay. So yeah, we can see 7 million colors within this range. We can differentiate like up to 7 million colors in this range. That's a crazy high. And like I said, this is only good in younger children. Your best hearing that you have is when you're a young kid. And from there, it's just a downhill slide for the rest of your life. And we're going to talk a lot more about hearing damage on day 3. This is a big deal to me. So it gets worse with age. But here's another a little caveat here. We don't hear all frequencies equally well. We're going to dive into this quite a bit, but we'll come to that later. I just want to throw that out there for right now. But just kind of a fun experiment, because I always think this is like interesting just in terms of general biology, is to look, let's say, how do we fare, say, compared to a chicken or a cow? So here's what I have right here. I pulled this table out of some journal article online. I should have noted it. I didn't note it right there. But out of the gates, we can see there's already a couple things wrong here. What do we notice on this first one is that, like, so I copied this table verbatim, so I didn't change anything on this thing. But we look right here, we see a human is 64 hertz to 23,000 hertz. Yeah, not really. I know I can hear a lot lower than 64 hertz, and I know that I can't hear up to 23,000 hertz. This is like a little bit skewed. So I wish I had the actual chart to go off of, because I wonder if they explain this a little bit. But we can see that this is approximate, within reason, within, like, it's reasonable right there. But let's take a look at the dog. So this is my dog, Poppy, which she's around here somewhere. Poppy, my dog, can hear from 67,000 hertz or 67 hertz. I'm pretty sure she can hear lower than that, up to 45,000 hertz. So they can hear about double what we can hear as humans in terms of frequency range. So they're able to hear much, much higher. So that's why we have these things like dog whistles, right? So a dog whistle would be something that's like that's above our hearing range, but within the range of a dog's hearing that we use these things. And so like a dog whistle, I think goes around like 18,000 hertz or maybe 19,000 hertz is like what those are. So if we wanted to kind of like say, what does a dog whistle to a dog sound like to us? So if we were to say that, okay, a dog whistle plays at, say, let's just say 20,000 hertz, just to keep it simple. So the dog whistle squeaks at 20,000 hertz. It's about halfway of their human hearing range. So that would be us having a whistle at about 10,000 hertz. So if we had a 10,000 hertz whistle, that's about what it would sound like to us for what a dog whistle sounds like to a dog. And like we'll do some of these 10,000 hertz, but 10,000 hertz is pretty high up there. It's kind of annoying to listen to 10,000 hertz. So when we sit there blowing on our dog whistle, like, it's pretty annoying to a dog. So, and then we look at a cat. A cat can hear 3 times as high as us. Holy crap. That's amazing. We look at a cow. Oh man, a cow has us beat. A horse has us beat. A sheep has us beat in terms of range. A rabbit has us really beat. We're not looking so good in the animal kingdom here, right? We compare all these other animals, and we're looking at, essentially right now, we're just looking at mammals. And a gerbil, you can see, wow, or a mouse can hear up to 91,000 hertz. That's insanely high. That's like, yeah. Exactly. You're right. And so, yeah, so again, you hit the nail on the head. And so, yes, like, we're going to address that exactly, especially when we start talking about human voice too, because we're going to do a whole section on human voice, and we'll see that human voice correlates exactly to human hearing, exactly like we were talking about. And you're right, that's what gave us a massive edge. Is that, well, we'll say edge, but that's as us as being what's important to our species is communication. Communication is a really, really important skill to us. We need to be able to do like, well, you look at some of these other like animals here, and they have to like, they live in this like eat or get eaten kind of world. And there's a Louis C.K. skit a while back, like where he talks about that a little bit, where he's talking about, he's like what a massive upgrade it is that we don't have to worry about getting eaten anymore. Like we do, but not like as much as we used to, right? Back in the old, like way old days, you had to really worry about getting eaten. And so, whereas like what a massive upgrade that is to not worried about getting eaten like all the time. But you look at a lot of these other animals here, and they, of course, they correlate their hearing to, well, mating and communication, and also like food and well, like hunting, and also not and like predator prey kind of type things where you don't want to get eaten. So you have to be able to hear your predators and get away from that. So yes, that's a very big thing for us. And also kind of goes along with that. Like, yes, we put a lot of emphasis on our eyesight as a species compared to some of these other ones that they have good eyesight, but not nearly as good as we do. And we spend most of so we use kind of a combination between the two of these. But yes, that's very, very adept. And we'll talk a lot. Yeah, you're right. There's the little trick right there about we don't hear all frequencies as equally as well here. So good observation right there. But like, look at this mouse. Whoops, let's go back here. So the mouse is 91,000 hertz. That's just crazy. So that means they can be like, especially if we like along what we were saying, if they correlate the squeaks to that they're probably squeaking at these very, very, very high frequencies that we can't even perceive. So that they're communicating and we don't even know it. It's like those, like the mosquito tones, like on phones and that sort of thing that's happening above the range in which we can hear it. But we can also see that there's kind of a correlation between animal size and the frequency. So if we look at a mouse is super tiny. So the smaller it is, the higher the frequency that things seems to go. And if we look at like where we have an elephant right here. So an elephant can only hear up to about 12,000 hertz, but it can hear what we call infrasonic for us. So it means below what we can hear. So they can hear sounds below what we can hear. But we look at something like a porpoise. Porpoise can hear up to 150,000 hertz, and a bat and a beluga whale. And these are animals that tend to use echolocation as some of their communication and also like hunting mechanisms right here. We know that, of course, bats like use the echolocation to like hone in on like prey. Actually, I saw like years ago, I was on this sat in on this amazing AES talk, like at, I don't know where it was, but it was like this, basically it was on like how, like, I don't know what that talk was about. It was like on ultrasonic hearing or something like that. But basically it was, they did these studies on this bat, and then they had a praying mantis. So praying mantis are pretty badass little bugs, but well, they're big bugs, but they're pretty neat and like bugs or insects. I'll use insects. That's more proper. And so it turns out that the hearing of, say, praying mantis, they're not very good at hearing, but what they are really good at hearing is they're really good at hearing a particular frequency, and that frequency is the frequency of a bat coming down on them. And what it does is, interestingly, is it actually triggers them to pass out. So their best defense mechanism for a praying mantis is to literally pass out when a bat is coming in. So a bat, what they do is they echolocate, and they do these really high frequencies, and then they listen for the delay on and location on like localization on where it's coming back from, and it allows them to hone in. And apparently, like, what they do is they change their chirping, their call just a little bit when they're dialing in. So what they do, like these pings, kind of like a submarine does, they do these like pings, and then they find an insect, and then as they're dialing in and getting closer and closer to it, I don't know if they change their pitch or they change their tone, or they do something that changes their vocalization for this echolocation, so they can, when they're coming swooping in or right in on it, they can like really get close to it. Well, it turns out what the praying mantis does is right when they key in on that change or that pitch or whatever it is, or amplitude or whatever it is, as the bat comes in and swoops in, they literally pass out and they just fall. And apparently it's a pretty effective means of evasion for the praying mantis. So Yeah, so they don't hear very well, but they hear some frequencies very, very well, and that's this interesting, like, again, communication. Or another one, I in that same talk, I think they were talking about these like super rare frogs, and I always think that like when you hear about these like crazy rare species, say like in the rainforest or whatever, in high desert or tundra or something like that, they're like these birds haven't seen each other. We haven't seen one of these birds in 50 years. I'm like, how are they mating if they can, if like we don't ever even see them? How are they even finding each other? Well, one of the interesting things about like in the rainforest in particular is like they've got these frogs. I mean, they did the spectrum analysis of all these of like, if you've ever been in the rainforest in the night, it's loud, like crazy loud. Like, I mean, you've got monkeys and bugs and birds, and I mean, well, not so many birds at night, but like the jungle is a loud place, and like, and you're like, how in this cacophony of just chaos, how do these like rare insects like that, or like or rare mammals, or even rare frogs, or snakes, or any of these amphibians, how do they find each other, reptiles? Well, it turns out these particular frogs, what they do is they chirp, and they have hearing, just like we were talking about with the humans, that they chirp and they hear at a very, very, very narrow band in the frequency spectrum. So even though to us it sounds like this huge cacophony of sound, to them it's almost silent, and they can just hear each other talking almost plain as day across it. They have like, they're filtering out the rest of the sounds, and they're able to hear really well in these narrow bands, so they can actually hear mating calls across like whatever range that they can actually speak, and you can actually find each other, which I think is just really cool and really fascinating stuff. So this is, yeah, kind of interesting. We can see that the smaller the animal, the higher the frequency tends to be, and the larger the animal, the lower one, and that kind of again correlates with what we believe. What I think is interesting down here is when we get kind of like out of mammals, we start looking at like goldfish. Like goldfish can hear from 20 to 3,000 hertz. That's pretty not so good. So you can see that fish in this particular reason right here, they don't really use hearing as part of their main sensory systems. They do have a hearing system, but it's not very good. But for me, one of the things that I'm sitting here going like, wait a minute, how do they know this? Like, right? So when you do a hearing audiology test, you do your little hands up, and you can say like, yes, I can hear, I can't hear. And like with a lot of these, I'm sure what they're doing is they're doing like feeding, feed type things, or like in a mouse they can probably hook up brainwave, like actually do some surgical sensory type stuff that they hook the mouse up to. But when we start like when we're getting into these like catfish and stuff like that, you can't train a catfish to like push a button to get the treat if it can hear a thing, right? Well, at least I've never tried one. I've had some goldfish in my life, and they're not easy to train. but um but I imagine what they do is they put up probes in their brains, and they can actually light it up when they hit like a frequency. So I'm curious how that kind of stuff works out. Same thing with like tuna and like bullfrogs and tree frogs. So they don't have very good hearing. But again, it's a loaded same thing to saying it's 100 to 3,000 hertz without knowing all of the what's going on there. But canaries, what's interesting is we actually, like, compared to these, we actually hear pretty well. We do have the bird. We have most birds beat. We can actually hear better than, like, when I say better is a loaded word. We can hear a wider range. That doesn't necessarily mean we can hear better. We can hear a wider frequency range than these other birds over here. So kind of interesting stuff though. So that the birds actually, like, and parakeets don't actually use a lot of high frequency stuff, even though they have a lot of high frequency content. They're not listening to those super, super high chirps up that they've got going on up there. Pretty cool stuff. Okay, so that kind of gives us a concept of like frequency range. How wide of a frequency are we able to hear from the lowest to the highest? And again, like, it's important that we understand that it's not all frequencies are the same, but that's kind of gives us a range. Now let's talk about amplitude. So this is going back to why we were talking about decibels. So decibels are, we can hear a massively wide, like high scale from quiet to loud. So we can perceive like a 1 times 10 to the 12 in intensity, because if we recall, 1 watt per meter squared is what we call the threshold of pain, and 1 times 10 to the negative 12 watts per meter squared is what we call the threshold of hearing. So that means the range is 1 times 10 to the 12. And if we also saw in terms of pressure, we saw that 2 times 10 to the negative 5 is the threshold of hearing, and 20 pascals is the 20 pascals is the threshold of pain. That range is a 1 times 10 to the 6th in pressure. So we see that these two are like, there's a massive range in terms of amplitude that we can hear. So intensities can be, in terms of pressure, is energy per area, which is watts per meter squared. So those are supposed to be squared. And then pressure is in force per area, which is Newton per meter squared. So and like we kind of mentioned like that for us, like measuring intensity is very difficult, but measuring force, like measuring pressure is something that we can do. So most tools that we use, we're going to measure in this area right here, which is going to be this one, which is the 20 log type stuff. So that's when we use the 20 logs when we're talking about pressure, which is force per area, not energy per area. So, okay. So we're going to spend more time talking about amplitude as we go along here, because we're going to use decibels quite a bit coming along here. But if you recall, just going back just as a quick little trivia bit, when we talk about decibels, remember, decibels is always a comparison. And when we say dBSPL or dBSIL, what we're comparing is this, like we're comparing it to the threshold of hearing. So that's what we're talking about when we start talking about decibels here. All right, let's talk about some anatomy. Let's get into this stuff. So when we talk about the ear, the human ear, we usually cut it up into 3 sections here. And so if we cut it up kind of like loosely, like right here, we're going to have the outer ear, the middle, and the inner. And, well, and then you can see that this is the skull. This is kind of like inside the ear. And then we have like, well, let's just get in and we'll talk about this thing. So let's talk about the outer ear first. So the outer ear is this basically a passive system. So actually, let's go back here and look at this diagram for a second. So if we go right up to here, this is the tympanic membrane, the eardrum. So let's go up to right here. So we'll consider the middle. The tympanic membrane is like the divider. So you could say, well, is it part of the middle ear, part of the outer? We'll just define it as being part of the middle ear, because what we'll do is we want to use this as part of the outer ear. So this is our ear like pinna, and then this is our ear canal right here. So what we say is that the pinna or pinnae is when we're talking about that's these guys right here on the outside of your ear. It's the cartilage-filled thingy on the side of our heads, and it aids in funneling sound and localization. We're going to spend a lot of time talking about localization too. That's next class. Localization is how do we define where something is in 3D space? And if you think about this for just a moment, it's pretty fascinating that if you close your eyes and you have a sound generator, say you have somebody talking and walking, that you could close your eyes and you can pretty accurately predict where they are in space, like how far away and where they are from you, and that's what we call localization. So, but we've got these things out here, and for a long time, scientists or biologists weren't really didn't really understand what the purpose of all these little folds and all this kind of stuff is. And it turns out it's pretty useful in terms of, well, it does 2 things. It funnels your sound. So if you happen to be on speakers right now, you can cup your ears, and what it does is by doing this will actually allow you to it gets louder. And if you're on speakers right now, even or if you're not wearing headphones, if you put this on and do this right now, you can actually hear it. It changes the timbre, the quality of sound changes, but you're able to hear a lot better. And you're like, whoa, I can actually it funnels the sound into my ear. Basically, you think about the old timey movies where they have the person who has hard of hearing, the old timey hearing aids was like a horn, and basically it allows more sound to get collected in and funneled into their ear. You lose the localization, but you're able to hear what's happening better. But in fact, I worked with this one producer in our in our studio years and years and years ago, and he would sit at the control room, he would sit at the console, and he would do this so he could hear a lot better. Basically it aided him to he felt like it helped him focus on the sound. So we'd have our music blasting and stuff like that, and he'd be sitting there at the console going like this so he could really focus in and hear it. But the problem is, even if just going like this, you can hear that it changes the timbre, the quality of sound changes. And so that's a bad habit. And also it's one of those things if this is your baseline of hearing things, then this is going to sound weird. So that's a bad habit. And I was like, ooh, I cautioned him. I was like, but he'd already had built into this habit of doing this before he was in our studio. And so he was just that's how he would listen carefully to mixes when he was mixing. And I was like, ooh, I don't know. That's a bad idea, man. You're going to warp your perspective there. So, but if you always listen, if you do this all the time and listen to it, then that does work. But kind of interesting. So yeah. So asking about would getting rid of the college piercing affect this at all? Yes. A cartilage piercing, yes, in very, 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 very small amounts. But the cool thing is your brain is pretty adaptable. You can adapt to things. And so even if it does change it, your brain will adapt to that, and you can adapt to the new normal sort of this thing. So, and the truth is, it does help, but if you were to Van Gogh style and just lop your ear off, you're gonna be just fine. You know, it makes wearing glasses a little bit more challenging, but you can survive just fine without having this. And so it does help with localization, but you know, even all these little tiny folds and everything, they do actually influence how that works. And this is actually an interesting part of like, well, like in VR and 360 and three spatial audio where I'm working right now, we can actually, well, I guess I'm gonna save this discussion for later. Let's save this discussion for localization when we talk about 3D audio and how that works. But yes, that's a great question about like, yeah, if I change this. So if, you know, if you like, whatever, if like somebody Mike Tyson me and bit my ear off right here, yeah, my localization might shift a little bit. It may not be quite as good, but you know, you'll be okay. And for the most part, like that's for us in our human like world, that's not such a big deal for us to like lose a little our localization. Our localization is pretty crummy compared to say like a deer or a mouse or some of these other animals that really have to localize. And in fact, an owl has insane localization. Their ears are actually offset. One ear is higher than the other, and some of the way that their feathers are positioned on their face act kind of like a pinna. So they are like owls are insanely good at localization because that's what they do. They sit up on whatever light poles and like be able to like hear a mouse rustling out in the field like whatever a couple hundred meters away, and they're able to localize that thing. And like they're insanely good at like owls are that's their jam. So auditory canal. So the auditory canal is just this. It's just this tube right here, which is like, you're like, well, duh, it's just a tube. Not so. It's actually really interesting. This tube right here has some very, very important resonant effects. And look, we'll talk about that, well, coming up soon when we start talking about pipes and voice. But basically, if we look at this thing, like if you ever blown in, say, a Coke or like a soda bottle or a beer bottle or any kind of like bottle, and it has it has a particular frequency that it resonates at. Well, so does this ear canal right here. So this ear canal resonates at a particular frequency, and it just so happens that that frequency that resonates at is about 3 kilohertz, which is the articulation range of our voice. So that's all this stuff right here. So what this does is enhances our hearing because it resonates. It sets it into sympathetic resonance. It resonates at the frequency, which gives us hypersensitivity at certain frequencies. And that frequency ranges around between 2 and 4 kilohertz, which again is like the articulation range of the human voice. So that we see that this is really, really important. The length of this and the kind of the shape of this thing are really important. Even though it seems like just a tube, it's just like, it makes sense that you're like, okay, well, also I want to protect all this business, so I should hide it deeper inside the head, but inside the skull. But it actually has a lot of like a physiological purpose for this thing. So it's pretty fascinating stuff. Okay, let's move forward. So that's all I'm really going to say about the outer ear. We're going to come back and we're going to talk more about this when we start talking about localization and talk about the like this. But you're right, it is interesting when you think about like if you start doing stretches or if you start doing like interesting piercings or you know, some other kind of modifications, it will change your localization. But like I said, your brain will be able to adapt to that. For your brain is surprisingly plastic, malleable. So I don't know if anybody saw that study where like a guy was wearing like glasses that would flip the world upside down. And it took him like 3 days for his brain to start seeing everything right side up again, even though visually everything was upside down. So it's kind of cool how that works. Yeah. Physiology is an amazing thing. Let's talk about the middle ear. So middle ear is pretty important stuff. So the first thing we're looking at here is what we call the tympanic membrane right here. So the tympanic membrane is what we call the eardrum. And it's sealed up around here. And basically it acts as like a drum. Why we call it a drum. So it's sealed up here. And what it's going to do is separate, like keep stuff out of this area right here, but it acts as a transducer. So let's talk about this concept of what we call transduction for a minute. So I'm going to use this term a few times throughout the semester. So if you want to use this thing, the term transduction means changing of energy from one form to another. So if we talk about Newton's, whatever, I think second law, energy can't be created or destroyed, but only can change form. Well, when we talk about things like acoustic energy and acoustic energy is kinetic energy. It's air molecules moving back and forth. But what we want to do is we need to turn that into something that we can actually perceive. So, well, let's simplify things a little bit. Let's think about like a microphone. So a microphone is a transducer because what it's doing is it's taking acoustic energy and it's turning it into electrical energy. And it's by doing that by using the little coil of wire around a voice coil and then a permanent magnet. And then if it's moving in one direction, it induces current in one direction. And if you pull it, it induces current in the other direction. And then we create voltage and current, which that's how we do audio. That's how so then we can use an AD converter and do sampling and all that kind of stuff. But what we the point is that we're transducing from energy from acoustic energy into electrical energy, and a speaker does exactly the opposite. A speaker takes electrical energy and turns it into acoustic energy. But in the same, but really what we're talking about there is we're just changing the forms of energy. So we're moving from one kind of form to another. So if we think about this from the physiological perspective, biological perspective, what we're trying to do is we're trying to turn moving air into something our brains can understand. Well, what do we need to get to? Like, what's the medium that we need to, or not medium, but what form of energy do we need to be able to get to so that our brains can understand it? Anybody got any guesses? Electrical. Good. Nailed it. So our brains work on electricity. We're like it's an interesting concept, but yes, our brains are not that we're plugged in, but we use electrical impulses to like that's how our brain actually and our neurons work. So we need to convert acoustic energy into electrical energy in the same way that a microphone does. But we use a little bit different. Well, we use a lot different process than the microphone does. But the principle is the same. So we need to turn air moving back and forth into here, into these nerve bundles right here. So these nerves, this huge ass wad of nerves right here is what's going into the brain, and we need to convert this to these electrical signals right here. So that's what the role of the middle, or sorry, the inner ear is going to be doing, is this conversion bit. And we'll talk about that coming up in a minute. But the first step, what we need to do is we're going to convert acoustic energy into mechanical energy, or like kinetic, like moving energy. Kinetic means energy in motion. And then we could also say we have potential energy, which is stored energy. So what we need to do is we're going to keep it pretty simple and say right now we just want to move this into kinetic energy. So okay. Oh yeah, I'm sorry. I know it is. You're right. It is an interesting. Just to restate this. So the way I'm going to restate, like I'm always going to restate something because uh, whenever anybody asks a question on online here, it doesn't actually get recorded. So your voice isn't getting recorded on the recording. So I have to restate the question and answer it. So, or discussion, not even question or statement in this case. But yeah, so the statement was that it's interesting that like in early human times, that we were in early instrument times, like drums were probably likely the first instruments that we did. Well, first probably beating sticks together, but then beating, and then yes, doing a stretched animal hide over something created a resonance, and we're like, ooh, that sounds really cool. And then yes, so many hundred thousands of years later, we're like, oh wait, yeah, the same structure's in our ear. How crazy. Hence the term eardrum, which eardrum. I guess this is not the eardrum, it's the eardrum. So my typo there. But yeah, it is fascinating. It's crazy how that thing works. So then we get to this thing. So let's think about this. The sound comes in here, it resonates in here, it pushes and pulls on the tympanic membrane here, and then what it's going to do is going to push and pull on what we call the ossicles right here. The ossicles are the smallest bones in the body, and what they do is we call this the malleus, the incus, and the stapes. Those are like the technical names, and we also sometimes you see the hammer, anvil, and stirrup. So this is the hammer, the anvil, and the stirrup. This one obviously does look like a stirrup. I don't quite see the hammer and the anvil, but not my thing. I didn't quite go with it. I don't quite understand how they got that shape, but whatever. Somebody along the line said that's what they call them. Then the name stuck. So we could say the malleus is the hammer, the incus is the anvil, and the stapes is the stirrup. Cool. These ones are kind of like, that one makes a lot of sense. Stapes is stirrup, but incus and anvil, you just kind of have to memorize those ones. The other thing that's interesting to note here is that we see that this is a cavity in here. So this is an air-filled cavity. And these are not just suspended right here in free space. They actually have little like systems that hold on to these things that like kind of hold them in place. But this is air. This is an air-filled cavity in right here. And this is actually sealed up all around inside your eardrum right here. But then we have what was our eustachian tube. And this is what goes down in our nasal passage. And we've all probably had this experience where you go up or down an elevation And when we go up in elevation, the air pressure is lower. So therefore, what's going to happen is if I go up, like up to a really tall building, then what's going to be happening is I'm going to have higher pressure inside of here and lower pressure outside of here, and this is going to bulge out, and that can create some discomfort. And likewise, if I go underwater and I go down to the deep end and I hold my breath and dive, the water is going to be pushing really hard in here. So what I need to do is I need to equalize this by equalizing this on the front to the back. And because this is sealed up right here, we use the eustachian tube right here, which goes into our sinuses. And that's what allows us, and it's not always open. You have to kind of like for me, I have to if I rotate my jaw around, I can usually find a sweet spot where I can pop open my ears and release the pressure. So basically equalizes the pressure for the inside, the outside. And of course, if we get sick, so this eustachian tube, because it goes into your sinuses, this is wet and mucousy and warm and a great place for bacteria and bad things to happen. And also when we get sick, we tend to swell up. And when this gets swollen up, basically this ends up clogging up, and therefore it becomes very difficult to equalize your ears. And we've probably had some issues with that at some point in your life where you've had a stuffy head, and part of that stuffy head comes from not being able to hear very well because you can't equalize your ears very well. And there's even things like when you're a young child, sometimes developmentally, they'll actually put tubes in to keep it open so that because when you're growing, lots of things happen, it can push on that and it can make it very difficult for you to equalize. So they'll put tubes in to actually hold that open to make sure that you can actually equalize in and out of there. And, in some cases, if you get an infection, like I had one a couple years ago, this will get swollen up and then actually start to fill up with fluid in here. And that's bad. And it feels awful and you've got bad things happen. And yeah. And so actually somebody just said somebody had popped their eardrum. That's you don't want to do that if you can help it. That's a bad thing. So because you can tear your eardrum and it can heal, but this is a pretty sensitive structure there. And if you get scarring on here and if you get some issues, it will shift the way you hear. Again, your brain can hear, you can adjust for that, but it's still it's not going to be as thin. If you get scar tissue on there, it's going to change the ability, how well this thing is going to be able to move back and forth right there. So, and if you've ever been, with a stethoscope, if you've ever had not stethoscope, but I can't remember what the scope is, but the ones that the doctors will look in your ear and they can actually see, because this is so thin, it's almost translucent. They can actually kind of see through it. So you can actually see liquid down in here when I had my ear infection. So kind of interesting though, but this is the air filter, but it's just important to know that this is it's completely sealed up. It's not like a free floating diaphragm. It's sealed up all around in there. And that's why we need the eustachian tubes right here to go into your sinuses to help clear that out. Gotta keep an eye on time here. Cool. Okay. So let's dive into a little bit more. Let's look a little bit closer about the ossicles here. Yeah, tinnitus. Cool. So let's talk about the ossicles. So what the role of the ossicles are here. So this is kind of like a thing taken off here. But ossicles provide mechanical amplification to aid impedance matching. Oops, not impedance, it's impedance. All right. Well, I've got a few misspellings on this thing. I'll go clean up those my slides here in a little bit. But let's think about we're getting a little ahead of ourselves right here. But the eardrum is air. So the eardrum is connected to air, but inside the cochlea, which is the snail-filled thing right there, it's filled with liquid. And what we need to do is we need to actually the technical term for that is what we call an impedance mismatch. So if you've ever been even in the bathtub or at a pool and you go underwater, water has a much higher impedance than air. So what that means is that if I'm screaming, if I'm playing my drums outside at the edge of the pool and I go underwater, as the sound as it travels through the air, it's going to hit the surface of the water, and most of that energy is going to reflect. Only a little bit of it's going to get down into there, and so that just get down into the water. And so if you underwater, you can hear underwater quite well. And in fact, I used to be a swimmer in high school, and if I used to swim at up in Fort Collins, would swim at the pool, and they would have what do they call it? Synchronized swimming before our practice. And so they would have underwater speakers. And if maybe if you have any synchronized swimmers in the house here, it'd be interesting to hear what you have to say about it. But for synchronized swimming, they have speakers above and below water. So when you're underwater, you can hear. And if you have an underwater speaker, you can hear incredibly well the music. And so we would actually be able to hear it. And it's really cool to be able to hear music underwater. But if I'm playing music above water through a speaker, just pointing it at the water, you'll hear just a pinch of it, and it's kind of muffled and weird sounding, but most of the sound is going to get reflected off the surface. And the reason for that is because we call it an impedance mismatch. We're going to see more of this impedance mismatching. We talk about things like cooler air and diffraction and refraction and all this kind of stuff happening. Actually, not diffraction, mostly refraction. But we see that basically this impedance change, when there's a large impedance change, it doesn't actually transfer the energy very well. So when the energy, it doesn't pass into there. So in other words, if I have the cochlea, which is what is filled with it, if I just had the eardrum as the cochlea, most of the sound would just bounce off the cochlea and never actually go into our brain and be able to hear it. So what we use the tympanic membrane as an impedance matching tool, essentially like a mechanical amplifier. What we're going to do is we're going to take a huge tympanic membrane and we're going to focus that energy down into a tiny, 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 tiny area. So in the case of this tympanic membrane right here is 80 square millimeters. I don't know why my subscripts are all bent out of shape. Whoops, out of shape here. But then we have the oval window. The oval window is how we get into the cochlea right there, and that's where the liquid is. And so we go from 80 square millimeters down to 3 square millimeters. So that's a 80 to 3 ratio, or 27-fold amplification right there. So it's increasing. It's like, you can think of it like a funnel. It's funneling the energy from 80 down to 3. So it's boosting it by 27 times. Like, that's how much it's getting in there. So that's the whole point. And what these do is these are the Hamel Anvil Syrup. They're the ones that provide this like mechanical amplification to do this. They're the ones that actually like provide that amplifier. They're like the levers between this. And so they're helping to do this. It's not just this. There's also like I don't have it, but if you think about like a seesaw, right? And if I have a seesaw with a point in the middle, it's equal on both sides. But if I put if I move the fulcrum point over to one side, it gives us a huge mechanical advantage. So say you're trying to like pry something out, you like a pry bar. So a pry bar is where you take a lot of mechanical advantage and like a lot of motion over here and a small motion over here with the fulcrum, and it allows you to put a massive amount of force with this. So we've got this like tympanic size difference, and then we have the mechanical, like it's acting like a pry bar on this, that it's going to give us between 35 and 80 times the force, which is humongous. So that's how we're actually able to focus this energy. And that's why our hearing is so sensitive, is because our eardrum is so big and so small. And then we have mechanical advantage that it funnels this energy in there, and we're able to hear really, 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 really quiet sounds. So it's pretty fascinating stuff there. Cool. Yeah. So that's the key takeaways here is I want you to it provides amplification and aid to impedance matching. As a quick little side bit of trivia right here. So these are like the kind of the support muscles that hold these things in place. But what's cool and kind of interesting is these can actually seize up. They're actually muscles. So they can tighten up. So you actually have a volume knob on your hearing. And this is something that we kind of know. So when you go into a loud situation, what they do is to protect your hearing. Because what we want to do is we want to be able to protect our hearing is incredibly sensitive. In the same way that our eyes will either dilate or constrict, like your irises will dilate and constrict. Well, we can do the same thing sort of idea. So if I go into a dark room, my eyes will dilate to become more sensitive. And when I go into a bright area, they constrict, and they're to protect my visual system. Well, we have the same sort of concept happening right here. These muscles right here, they can tighten up and essentially turn the volume down on your hearing. And then if you go into really quiet, these things can really relax and they can open up, and you can become much more sensitive. So our hearing is dynamic, but the problem is that they don't move that fast. In the same way that if you have your eyes closed or whatever, you turn on the lights in a dark room for a long time, you're like, it hurts. Well, the same thing happens with your hearing. Your hearing is wide open. If I start playing blasting with a loud sound, it takes time for these things to constrict. And so things like guns and like highly transient sounds, they're really, really bad because they get through. It's like they're like a compressor, like if you want to think about it like that. These things are like a really slow attack and slow release compressor. So if I have something like a gunshot or a snare drum, snare drum is a good example, something highly transient and loud, that your eardrum doesn't have time to do that all that energy gets pushed down into your cochlea, and then that's where bad things happen and hearing damages happen. Of course, these only work to a certain point, so you still have to wear earplugs when you go to shows or when you're in a loud environment for a very long time. We'll talk about that later too, though. But yeah, and then also, it takes a while for these things to happen. So I'm just gonna leave it at that for right now. Okay. Cool. Let's talk about the inner ear. This is where I think things like get really stinking fascinating. This is like where the magic happens. We call this one like the the body's microphone. So that's this business right here. So when we talk about the inner ear, we have the cochlea, the semicircular canals, which are up here, and then we have the auditory nerves, which are all this huge wad of bundles right here. Actually, it's this bottom one right here. I should have shown this down here. This is right here. These are our balancing nerves. So I'll get to the cochlea here in just a minute, but let's just talk about these semicircular canals. And like, it's kind of hard to tell on this drawing right here. And it's really cool. When we're in person, I have an ear model where you can pull it apart and get a sense of the scale of this thing. But if we look at this thing, we have one that goes like, we call this semicircular because they're pretty much like semicircles. We have one going up here. We have one going around in this axis and one going kind of in the back right there. And it's kind of hard to draw this one right here in 3D, but it's going back. And what we can say is that these are like essentially like one's in the X, one's in the Y, and one's in the Z. And the semicircular canals are what we use for our balancing mechanisms. And it's really interesting. And I like why our balancing mechanism is tied to our hearing system, I don't know. It's just the way it is. It's just kind of the way things evolved. And there must have been some reason. I mean, part of what I can gather here is like, if you look at this, we want to bury this deep, thick in our skull, right? We want our balancing mechanism to be usually related to our head because that's where all of this like sensory information is coming in. And so we want our balancing to be like related on our head. We'd probably want our balancing like mechanisms to be on our shoulders because we're moving our shoulders around all the time. So it makes sense. And also that it's like located deep in the skull, thick in this really encased inside of this thick skull bone material. So it's a pretty good protective mechanism in there. So besides that though, I can't say. And also the fact that we want it to be stereo. So we want to have like a balancing mechanism on our right and a balancing mechanism in our left that gives us a better resolution on to keep our orientation. But inside of these semicircular canals is fluid. And they've got these little tiny hair cells that are all like that line this. In fact, it's not all that different. I mean, they work different, but it's the same concept, is that I have hair cells inside of the cochlea down here. But I've got these little tiny hair cells in here that they're like sensors. And when they're in liquid, they're firing off saying, hey, I'm in liquid. And what would happen is if I rotate, if I go to my side right here, the fluid is going to flow down to this edge over here. And then all these nerve endings right here are going to fire off saying, hey, I'm this way. And then on my other ear, it's going to be flowing the other direction. And with that information, your brain can interpret that saying, hey, I'm sideways. And then going up and down, like it gives you a pretty good sense of orientation. But things like when we go spinning around on a ride or something like that, and we jump off it, what it does is when you're spinning around really, really fast, what it's doing is it's distributing the fluid around in that space. And then when you stop, it takes time for that fluid to like flow back down into like center itself. And when it's doing that, your brain sends mixed signals and you can't tell which way. And that's when we get dizzy, right? When you run, like we do the silly one where you like basically put your head on a baseball bat, run around and you try and run and everybody falls over. Because basically your brain is getting mixed information. Your brain thinks that that's the ground, but the earth is actually over there. And so it makes you fall down. It's all sorts of, it's all fun and game when it's fun and games. But when it's also not fun is when you get something like vertigo. So when vertigo happens is when you get misinterpretation. It could come from sickness or from genetic, can be all sorts of different kinds of things that cause misinformation to happen in your semicircular canals that result in you not being able to have very good balance. And I had it not that many years ago. I got like that same ear infection I was just talking about. I got some pretty nasty vertigo, and I was actually in a band at the time. And so what I would have to do is I was playing bass in my band, and I was have to lean up against my cab so I wouldn't fall over because I was I would be in the middle of like practice and I would almost fall over and hit the ground, and you're holding your instruments and stuff, like sucks. So and for some people this is a very chronic condition and it's awful to have it. So for me, fortunately, it was just a temporary situation, but for some people they live with this for a long time as a chronic on and off condition or as like an all-time condition. And it can be really, really, really rough. The other thing I want to say about that though is like what's interesting is as you get older, that fluid in there becomes less viscous. And therefore, what ends up happening is it resets itself slower. So, and the result is I get motion sickness a whole lot easier as I've been getting older. I hate it. I go to the freaking Elitch's and I can't ride any of the rides anymore because like I get so motion sickness. I'm so pissed about it. It sucks. I love riding rides. Like I don't know why, but I can't do it anymore. And it makes me so sick, which is also kind of funny when you think about it. You're like, well, wait a minute. Why does misinterpretation of this make me vomit? That doesn't make any sense, right? Like why, why, like my body's like, I can't tell which way is up. You should probably puke. what? Like, I guess, like, the best I can tell is your body's just like, you know what? Let's just hit the reset button and start over. So like something's not right here. Get it all out. That's the one thing I can do. And so, but it's just weird. Like, you're like, why does motion sickness lead to vomiting? It just doesn't make any sense. So, cause like, it's not like you ate something bad or like food poisoning, but one of those like mixed signals in the brain cause you to vomit. So interesting. Also, what's interesting is like, if you go into free fall, what happens is, like if you've ever gone over a car, where you go, whoa, or done something like bungee jumping or even skydiving or something like that, when this is going up and it's basically, all the fluid distributes itself right there. It's kind of panicky because that's your brain telling you I'm falling, right? And that's what's happening there. But if you imagine this, if you're on the International Space Station, this is what's happening to you all the time. And in fact, truthfully, what you're doing is you're falling. Like if you're in orbit around the Earth, what you're doing is you're falling to the Earth, but you're traveling fast enough that the curve of the Earth is like keeping you, like your centrifugal and centripetal forces are equalized to each other. But the result is you feel like you're falling nonstop. This is one of those things that they don't really talk about, like when they're talking about space travel. But if you're on the space station, you feel like you're falling all the time. You're like, but you're in one spot just going, but I'm okay. But my brain is telling me I'm falling. How weird would that be? Like, that's one of those things that like be probably pretty weird. And it does cause people to puke a lot. Like space sickness it causes a lot of people to puke. So yeah, crazy. So I've been listening to a lot of like space stuff lately for whatever reason. I just listened to this, don't have time to talk about it now. I've been reading a lot of books, like a lot of audiobooks. Because I'm working in the shop so much. So I've been plowing through almost a book every other day right now. So I'm just plowing through books. Cool. All right. So let's talk about this cochlea business, because this is like really important to understand how this thing actually works. And this is a really crummy picture, so I apologize for this, but this is the best one I got for right now. What we have here is this thing that looks like a snail shell. But if we look inside the snail shell, it's actually cut up into a couple different like tubes. So we can imagine this being a snail shell going all the way up. So if we look at it right here, it's like a snail shell. But if we were to look at the cross section of the snail shell, it's actually like cut up into tubes. And so what we see here is we have what's called the stapes right here, the stirrup, and it's pushing on the oval window. The cochlea itself is actually a hard material. So if it's not bone, but it's like a bone-like material. It's like it's rigid. So it's not squishy or anything like that. This is all rigid. But what we do is we have our oval window and we have our round window, and these two are squishy. And this thing's completely filled with fluid right here. So if we think about what we're going to do here is we're going to push on the stirrup right here, and we've got this little arrow, this black arrow. So this is the tube. We've got this third tube right here, but this is the top tube, and we'll call this the bottom tube. The top tube, bottom tube. It's kind of hard to see it here. Top tube, bottom tube. So it's going to what happens if I push in on this, because liquid doesn't have a lot of give to it compared to air. So what's going to do, and we think this is like think about like a brake line. So if you push on your brakes in your car, what it's going to do, and if you have some like mechanics, if you've ever played with brakes before, basically you've got like brake fluid that runs through your entire brake lines in your car. And when you push on the brake pedal, you have a motor that assists on it. But what it does is it pushes on that fluid, which goes all the way back into your brake pads and your calipers and squeezes them. And so we use the brake fluid because it doesn't expand and contract very much. That's why it doesn't freeze. It's it's kind of nasty stuff. But in here, it's like essentially just like, we'll say it's water. It's not quite water, but it's pretty close to water. If I push on this, the water it's gonna push this direction here. It's gonna come up here. It's gonna push up here. It's gonna come up here, and there's a little window right here. It's gonna push down here, push down here, and push down here, and this is gonna bulge out. Now, if we think about how sound works, sound is pushing and pulling on the eardrum. So it pushes on the eardrum. It's gonna push the stirrup down. It's gonna go all the way down here, and the round window is gonna bulge out. And then when a rarefaction hits our eardrum, it's going to pull in. And so the stirrup is going to pull out, and then therefore it's going to reverse direction right here. So this is going to pull this direction, pull this direction, pull this direction, and the round window is going to suck in. So really what's happening is the sound is pushing on our eardrum, and the round, which is then pushing on the oval window, and the oval window and the round window are going to be moving in tandem. So when the oval window pushes in, the round window pushes out. When the oval window pulls out, the round window pulls in. So basically it's moving back and forth. And so basically what we have happening in here is this liquid is oscillating very quickly back and forth along these tubes, and specifically along this membrane right here. Actually, it's this membrane right here. It's going to be like this. It's going to be pulling back and forth and back and forth and back and forth. But the result is that it's going to be like vibrating this one piece of this well, we'll call it the basilar membrane here in just a minute, but it's basically going over the top of the bottom of this basilar membrane. And that is going to be what's going to clue us into how we determine what frequencies are sounds. So here's kind of another cross section of it right here. So this is like kind of a three-dimensional cut of this thing here. We have the top, the bottom, the organochordae, and then inside here we have the cochlear duct, and then right here we have the basilar membrane right here. So if we think about this, if this one's pushing in, this one's pulling out, if this one's pulling out, this one's pulling in. But we can see that we have what's called the basilar membrane here, and the basilar membrane is only exposed to the tympanic canal right here. So it's this, we'll say it's the bottom one. So this is the bottom one right here, bottom one right here, bottom, 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 bottom. And so that it's this basilar membrane right here is only exposed to one part of this thing. And that's where things get really interesting. So what we're going to do here, is I'm going to stretch this thing out. And usually when we talk about the cochlear membrane, we unwind this thing. And it's a little deceptive right here because they're showing it like a tube. This is from How Stuff Works from 2001. But it's actually, we know it tapers inside of here. So it's actually like, it actually tapers down, but it's drawn like a tube just to kind of make things a little bit easier to see what we have going on right here. So we have the oval window right here, and then we have the round window right here. So it's the same deal. When I push here, it pushes around here, comes back and pushes out right here, and then back and forth here. But what I want to focus on is what they're showing is these little lines right here. So these little lines are basically it's a gradient. And what we can say is that, like, if we think about these, let's think about like guitar strings, for instance. Let's just use that as an example. We'll think about these like stretched strings. That's not what they are, but let's just think about that for a minute. So if I have a long string, and we'll say that they're all under the same tension. So if I take a long string versus a short string, the long string, if I pluck it, will have a low frequency resonance. And then the short string will have a high frequency resonance to it. So what ends up happening here is that if I take a bunch of different strings and then I basically make it so that these are really short strings and these are really long strings, the short strings are going to resonate at high frequencies and the long strings are going to resonate at low frequencies. So if I send in a low frequency, if I push this oval like stapes back and forth at a low frequency, it's gonna swish back and forth across the basilar membrane here, but the rate at which this is going back and forth, when this hits, this is gonna start to vibrate, to resonate with the frequency that's actually happening. And what we're gonna do is we're gonna attach a sensor to this thing that says, hey, I hear a low frequency sound. And then if I attach sensors along this whole thing, I'll be able to say, hey, I'm listening to high frequency, I'm listening to low frequency, I'm listening to high frequency. And of course, when we listen to music, it's a combination of things happening all across this thing. Now, like I said, they're not strings, it's a membrane. But what we can say is it's a gradient right here. And so that this membrane resonates at high frequencies up here, closer towards the windows, and it resonates at low frequencies towards the tip, which is a little weird because if we look at this picture again, that what we're saying is that the high frequencies are coded here and the low frequencies are coded up here. It goes opposite of what the shape of what we would intuit on the shape of this. Even though the outside of the cochlea is tapering down, inside it's tapering out. So it's kind of hard to think about it like that, but that's what's happening. So, but the result is we get like what we have here is we have what's called we call place theory. So place theory tells us what frequencies are coded along the basilar membrane. So at high frequencies, it's going to be up here, but they're drawing these squiggles out like high frequencies are here, close, and then low frequencies as they go down here, low frequencies. And unwound, it looks like this. So we have high frequencies. So this is the oval window right here, and this would be the round window down here. And the high frequencies are coded for the high bit up here, and then the low frequencies are coded for these ones down here. And in fact, these are our hair cells right here. We'll see pictures of these here in a couple minutes, but these are the little tiny hair cells that sit on your basilar membrane and they wave back and forth. So when this is vibrating and this is oscillating right here, and this because of the resonance of this being coded, this little hair cell is going to wave back and forth and go fire, 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 and your brain goes high frequency, high frequency, high frequency. And if these ones are going down here, your brain's going to be going low frequency. So, and then we have this nerve signals, and we have like a lot of these nerve signals. That's why you have such a massive bundle of nerves coming off your cochlea right there. So let's take a look at this for a moment here. What do we have? 1206. Let me see. Let me take a look at my. Where are we at? Okay, yeah, we're looking pretty good here. So what I want to do here, and this is actually, there's a, like, it's kind of hard to see it, but like, so we, again, we see the big tube and the little tube, and we can see that this is our cochlear duct, and then our basilar membrane would be sitting right here, like sitting right here. And if we were to unroll this thing, so as our discussion was earlier in the class, at the beginning, we're saying that we can hear from 20 hertz to 20,000 hertz. So what we could say is, if I stretch this, actually, let me go back to this picture here for a second. Let's go back here. So I'm going to say that this is 20,000 hertz and this is 20 hertz right here. So we'll just to keep things simple, we'll just go with that. 20,000, 20. What's right in the middle? What frequency would you call the middle? Like, just roughly. So if, well, okay, let's even go with this. Let's call this 20,000 hertz, and we'll call this 0 hertz down here. What's halfway between 20 and 0? 20,000, I mean 0. 10K, yeah. So we'd say that we would intuit that this would be like 10,000 hertz right here. So, but let's take a look at what is actually plotted out right here. And it's hard to, it's not really drawn too well right here. Well, it's drawn pretty well. It's just hard for us to see it because it'd be a lot easier if this thing was stretched out. So we call this 20,000 hertz up here. And if we were to go to about, like, I'm guessing the middle would be around right here. Huh. Look at that. The middle is about 2,000 hertz. And then it goes down and down and down and down and down. That we see 200 hertz, and then actually it goes like 20 hertz. It's just going to be right here. So the result is, if we were to actually plot this thing out, this basilar membrane has a near logarithmic scale to it. Holy crap. Let's think about that for a minute. Our basilar membrane is plotted on a logarithmic scale. So therefore, that's why every single thing we use in audio is on a logarithmic scale, because the logarithmic scale correlates to the way our basilar membrane works. And this also explains our resolution. So at about 50% on the basilar membrane is about what we call the mid-range. So 50%, we'll say it's going to be around right here. Between 2,000 and 3,000 hertz, yeah, you'd sit there. If you're listening to a 2,000 hertz tone, you're like, yeah, that sounds kind of like in the middle. And then if I play something like a really high frequency sound, so like we could see that, like if I play something like, and so our resolution, what we're doing is we're spreading our resolution, we'll say from 1,000 hertz to say 5,000 hertz. Most of the range of our basilar membrane is from 1,000 hertz to 5,000 hertz. And that's because that's, again, going back to, this is where the human voice lies. Because we want really good resolution in this range right here. Like hearing above 7,000 hertz, that's all well and fine, but it's not really that important to us. Like it's not like that. Like if I roll off the frequencies at between 20, 30, if I roll off at 16K, I'm like, I can't really tell. It doesn't really make that much difference to me. It's not that important. And same deal is, I mean, I love low frequencies, but I can't very well discern low frequency resolution. So most of the range is spread around here because, again, it correlates to our vocal range. And that's what we want to see happen here, is that between 1,000 hertz and say 5,000 or even 7,000 hertz, we can say between 600 hertz and 7,000 hertz. That's where most of the range is. Of course, we can hear a lot lower than 600 hertz, and we can hear a lot higher than 7,000 hertz, but this is where we want most of our sensitivity to lie. And again, this is also just crazy. It's not perfect. It's not a logarithmic scale. It's pretty close. But it's close enough that's why when we look at any spectrum analyzer, it's always on a logarithmic scale, because that correlates to the basilar membrane. How cool is that? Like when math correlates to our sensory system, badass. So I don't know. I think that's just really, really, really cool. So that's a really important concept. So here's another visual of this thing right here. So we have our semicircular canals, and we call our basilar membrane right here, and then remember, it doesn't physically get bigger. What it does is the membrane gets looser as it goes along here. But this is an easy way to kind of think about this thing, so that as this thing vibrates, and we have the helicotrema. This is the hole that allows the fluid to pass through and go underneath it. So the result is that basically we can see that in about the middle of our range, we can see it's around between, between like 1600 hertz and 800 hertz. This is going to be what we call like the middle range of what we would hear. So I'm going to pull, like, this is my last slide. So I'm going to pull this up so you can see it because it's pretty cool. It gives a kind of a neat little demonstration. Where is my... Oops. Where did that go? All right. So what they did is they basically zoomed in on around the cochlea so we can see the basilar. What we're looking at is the basilar membrane right here. And what they're going to do is they're going to play some tones and we're going to see where it resonates on there. It's a simulation. This is obviously not, this is way overdone, but let's take a look at it. So it's kind of, so it's a simulation, but we see like we get the idea there that that's what's happening. And of course, it's much more complex. And the cool thing though there to note though is that when we say like high low frequencies, that basically these are happening at the same time. So when I hear a complex tone, meaning any tone that has multiple harmonics or any kind of thing that's not a sine wave, it's going to excite different areas on here. And of course, it gets more complex than this. There's other things like temporal aspects of it. So in other words, if this thing is exciting and I stop, does it keep vibrating? Yes. And so it takes time for it to recover. And so that there's like, if I play two sounds too quickly together, I can't discern them, like hear them. So this is what we call like the rate of perception. In the same way that our eyes can only see about 30 frames per second, our hearing, I don't know what the frames per second of our hearing is, but basically there's a recovery time for something to happen. And also an amplitude time. So if I hear something loud versus something quiet. So if I hear something very quiet, it's gonna vibrate just a little bit. If I hear something loud, it's gonna vibrate really loud. So it's a gradient. It's not just on or off. It says, "Hi, I'm a low frequency and I'm really loud," and then basically it's basically going back and forth and doing loud and quiet and also loud and quiet and frequency, which gives us sound that our brain is able to then like. All it's doing is basically, well, I don't have the slides up right now, but basically these little hair cells, they're firing, and then that's what gets, it's just raw firing of signals. And then your brain is able to decode this. And that's where the term psychoacoustics comes in, is our brain is able to decode all of these firing of these nerve endings and turn it into an understanding of what's going on in the outside world. And that is magnificent. It's just insanely cool. So, that's what we have for today. So like I kind of went through kind of a lot of stuff, but I think this is where it's like fun trivia. I think this is where like you start to notice it when you start to think about how this stuff works. You're like, I can really like relate to this information. So, yeah. So I guess that's all we have for today. So next class, what we're going to do is we're going to talk about the sensitivity, like Fletcher-Munson curves, and actually how these hair cells work. And then we're going to start diving into like hearing damage. And on localization. Localization is a big one. How we hear in 3D with 2 ears, which I think is pretty fascinating stuff. So with that, my friends, I'll go ahead and stop now, but I'll stick around for if we have any questions or anything like that.